I mean, I'll just tell you how Oorja Energy started. I mean, we three co-founders have been working in the physics simulation space for, I mean, everybody was, more than 12 years of experience. And we had our customers in different physics areas where for them to model the physics problems and also, come up with the optimum design was a big challenge. The reason was that all these physics-based models require a lot more expertise, and which often the designers don't want to get into those kind of details. Rather, they just want to experiment with their design and just want to see how their design can be optimized without getting into the technical details. So, being in the simulation software industry, we realized that this has been a big challenge, and we wanted to simplify this. That's how Oorja started. And the idea here was that instead of just using the pure physics-based simulations, if we can combine it with hybrid methodology, which is basically combining the experimental data, physics models, as well as machine learning methods, to give an idea to the designer of quickly coming up with an optimum design. And also, if you look at the traditional software space in this area, we can change the slides. So. Usually what happens is that you have a standalone software which you need to install in your system and then do your analysis. And if you want to share these models, what happens is that you need to share these files across other people just to see that how the simulation works. Now what we tried also to do is that instead of having it as a standalone tool which is installed in your system, we wanted to make it web-based so that you can bring your data, you can upload it, run through the analysis, you get a report out of it, and it's as simple as that. And when you want to share these models across others, you can just click on a share button with the email ID. They will get access to that project so that they can also go through what kind of a design you have worked with, and it is much easier for the collaboration. And typically if you look at, so the first problem that we started with, so the idea here is very general, that if we can simplify the complex engineering solutions by using this methodology. But first thing that we started with is batteries, because that is something that is very well suited for the approach that we have taken, because as you all are working in this area, that based on the operating conditions and also the manufacturing changes, you can see that batteries, operate in a very different ways. Their behavior is unpredictable in different situations. So that is what we are trying to address here with this methodology. So typically, if you look at the physics-based solutions, they are very accurate, but then at the same time, they require many parameters in terms of battery design as well as transport parameters to model these, and which makes it really challenging for the designers to understand their behavior. So what we have tried to do is we innovate certain experiments through which we can capture the behavior of the batteries with these parameters. Then we identify the physics parameters based on this, and that we use in the physics-based simulation softwares to do the predictions for the different conditions. As well as we train the machine learning model. So once you have generated all this data, you can train a machine learning model and look at what kind of variations the cells show under different conditions. So can we go to the next slide? Yeah, so the approach we have taken is something called physics-informed neural networks. So you are familiar with the neural networks, which are very familiar terms in machine learning space, and then we have the physics models. So what is the advantage of this physics-informed neural networks is that it requires less amount of data. If you were to just do the pure machine learning based model, it will take huge amount of data to train the model to do accurate predictions. But what we also try to do is we try guiding these neural network models with the physics-based constraints, which makes them more accurate. Because, for example, a very simple thing, if you just want to train a neural network model, let's say for a physics problem where the energy conservation is most important thing, because we know that physical law says that energy and masses are conserved. But if you just do a pure machine learning model, it is not going to respect that. It will just look at the data, identify the pattern, and give you a prediction. But these physics models will guide these neural networks to also respect certain physical laws which are a reality and making it more accurate. And that's the methodology that we have come up with. So the way it works is that you design certain experiments, you bring this experimental data, train make a physics-based model, and then using the neural network and the physics models, you try to optimize these parameters. And once you have got these neural network model, which is more accurate representation of the physics, you can now bring in your new parameters, new kind of operating conditions and parameter sets, and do a prediction for the battery. Next slide, please. So so this thing I have pretty much covered. So you define the properties for the cells, which are like density, specific heat, and things like that. You bring in the input data, which is experimental data, and then once we have trained these material models, you can create the different scenarios in which these battery packs are going to operate, and then you can analyze and optimize your solutions. So for that we have come up with different apps. As we are dealing with data, we have application for data processing, where when you do this, when you experimentally collect this data, they have a lot of noise. So what we also need to do is we need to clean them up. For that there is an application for the data processing, and then we have an application for storing the material properties. And then two major areas that we work in at the moment is the thermal runaway and thermal management modeling, as well as capacity degradation of the batteries. And at the same time, we have an application where you can, based on the vehicle drive profile, you can convert that to the battery pack current. And that will be used again for the predictive analysis of capacity degradation as well as the thermal runaway predictions. And here are a few examples where you can set up the model and you can initiate the thermal runaway in the cells at different places, and you can look at how it is propagating from one cell to another and how long does it take to propagate across the pack. And this is an example of a range prediction where you can provide this kind of a drive profile, and you can see that how the vehicle range as different levels of degradations gets affected. Because when you have new pack, your driving range is much larger than you would expect after it has degraded. And we can also predict that as the battery pack degrades, how the range is going to change over the period of time. Right, and this is about the capacity degradation prediction. So the first part shows that data cleaning. So you have the noise in the data, and then we have cleaned it up so that it is smoother for the machine learning operations, and then we try to train the degradation. And dots are actually the experimentally measured data, and the solid line shows predicted values from our software. So which itself tells that it has a huge accuracy. So we operate with the three different kind of licensing models: starter, accelerator, and cruise control. With the starter, you can do basic thermal management and degradation predictions, but with the accelerator, you can import your designs, and you can generate the drive cycles for the further analysis, and you get also the data cleaning applications. And with the cruise control, you also can perform the runaway analysis. And to more about the founders, I come from this basically physics simulation background, where I have been doing these simulations and developing the software for a company called COMSOL Multiphysics, where I was basically working in the area of structural mechanics and rotor dynamics, where we basically developed 3 products out of India office. Vineet, our other co-founder, basically was heading the Indian operation of COMSOL Multiphysics. And Prajakta was basically into the user satisfaction in COMSOL Multiphysics. And that is where we all three realized that probably we need to change things for the designers. And the Oorja started. Thank you all.
Thank you, Prashant. Thank you very much. That was a pretty concise presentation, and it just stuck to the time. Prashant comes all the way from Bangalore. Well, C3 is actually for predominantly Chennai guys, but Chennai guys, we are all very nice people. We accommodate other cities as well. As long as Chennai gets the top in IPL, we are fine with it. All right. Pradeep from Aerostovilas. I saw Pradeep for sure. Oh, coming all the way from there. Yeah, you got to design your micro turbines to run faster. So Pradeep, oh, these guys do some really interesting stuff. Rather than trying to complicate it for you, let me allow you to explain what they do. Um, they do operate in the EV area, but in a very different way. Pradeep.
Hi guys. So basically I'm Pradeep from Aerostravelers Energy. So we are working in really small gas turbine engines. So the micro comes from the fairly the basically nomenclature how the industry has named it. So we'll get to that. Yeah. So predominantly two areas that we're focusing on. One is power generation and second is mobility. And specifically in mobility, we are looking on the trucking areas as an application with micro gas turbine. So just before going into basically what is micro gas turbine, I would like to touch upon what gas turbines are all about. So gas turbines are basically engines that you see on your aircraft. They've been well proven, they've been working for many decades and basically transporting millions of people across. So that technology comes with a lot of reliability and traditionally with a lot of cost also. But what we are trying to do is right now take that, the base principle, work on a very, very simple structure and make it affordable across all platforms and other things. That is the major work that we are doing in. So, like I said, what we are focusing on is a 100 kilowatt gas turbine engine. Two applications, one is the trucking and then the power generation level. And this will be fairly the first product that we'll be aiming for, and then moving on, we would be looking at higher power levels. And one of the major aspect of a micro gas turbine is basically it's also extremely modular. So fairly I can have like 3, 4, 5 running that I can generate close to about even 1 megawatt. So with the same capacity, basically I don't need to innovate newer products rather than build in on modular levels. So I don't have a pointer. Yeah. So basically the main focus over here was basically to see how we can use micro gas turbine to build the mobility segment. So what we propose is more of a hybrid system, and the reason, we have a couple of reasons why we are moving into the hybrid systems rather than basically an EV or a battery electric vehicle systems. One is the commercial vehicles earn their revenues through carrying tonnage or carrying weight or carrying volume. Fairly, that gets affected quite significantly when it comes to batteries. So we propose basically a very, very lightweight, compact system, which is our gas turbine engine, which generates onboard power. There is going to be a small amount of battery. So if you can see here, this is where the micro gas turbine sits. This is basically a small buffer battery, say about 20-30 kilowatts. And here you can see there are two boxes, which is basically fuel tanks, and the main motor that sits in the center. The yellow thing is the motor. So what ideally we basically do is to ensure that there's enough power on the truck and enough range, and still take advantage of the electric powertrain where the efficiency is extremely high. So this overall configuration can give better efficiency. It can be at par to your grid costs and grid level costings, plus the heavy reduced capex because you're not using a huge battery over here. And the added advantages of you don't need megawatt levels of charger for doing fast charging and other things, whereas the onboard system takes care of all the power requirements that are there. Since you're not idling anywhere because your electric motor is taking care of all your movement, the micro gas turbine kind of calculates how much energy is required and then starts and stops accordingly. So so the micro gas turbine concept is kind of laid out that way. But in terms of, as a company, we have also a couple of innovations that we have kind of come up with. One is, like I said, traditionally gas turbine engines have been very, very expensive because they use exotic materials. So our design allows us to use basically something what is called a turbocharger material. So turbochargers have been in ages in automotive diesel engines. Now even in petrol engines, they have turbochargers that have been built and other things. So we kind of use the manufacturing and the materials from the turbocharger product. So kind of our turbines are will be as competitive as any diesel engines that is coming into the market. and second is the performance, and in terms of the running cost, the maintenance, and there are multiple innovations that go into it. And one of the most limelight area I would see is basically our patent that we hold, which is called the swirl mesh lean direct injection system. So the right top image you see is actually a test sector of our combustion. So one of the significance, anybody who's in the chemistry kind of understands that the difference between a yellow flame and a blue flame. So when you burn something which gives out a blue flame, that means the emissions are really, really low. There's no incandescence or sooty flame that comes out. So that is what you're seeing over there, the blue flames. So that is basically an outcome of our technology, which is on the combustion level. So we have extremely clean combustion with our micro gas turbines. So without any catalytic converters or post emission treatment system, we'll be putting out an emission which is more than 100 times cleaner than the current BS6 norms. Yeah. Thank you.
Thank you very much. The way I understand, oh, by the way, I'm sure you guys have questions for many of these people. We have enough time after this. It will be probably easier if all these guys can be seated somewhere here and you shoot questions at all of them together. The way I understand Aerostovilas as a business guy is, look, leaving aside the technical stuff that he spoke, so these guys are using the aircraft engines, but most importantly, it's fuel agnostic, which means while on one side you have EV, which has to go from what we are today to a completely new system, they can put in an internal combustion engine today, but the key value is the same engine can use a whole range of fuels, which means I can put biofuel, I can put natural gas, I can put bio-CNG. So that's suddenly giving me a pathway which is hopefully much faster, or at least a transition pathway before the whole world becomes EV. That's the way I understand. Please do let me know if my understanding is right. That's the business case I see for them. That's what I see. Abhinesh from Blair. Yeah, hi. So Abhinesh, these guys are working more on the motor side. We'll be very delighted to hear what you have to say.
Thank you, and good morning, everyone. So I'm from Blair. Blair is a technology-based company. We work on powertrains and control systems. Blair we started in 2014, and we've been in research and development on different types of powertrain architectures and control systems. So predominantly we were focused on hybrid architectures. Hybrid, like Nasi was saying right now, ICE plus electric is what we started off with on a motorcycle concept back in 2014, and from there on, we've grown from just on the motorcycle to two-wheelers, three-wheelers, and commercial vehicles right now. And right now, we have not 5, we have around 6, 7 technology patents, out of which 4, 5 are granted. There are 3 more that we are filing on the architectures and control systems that we are working on. So, as a technology company, we work on innovations. We'll work with OEMs as an R&D partner through joint development programs, and then get the product out in the market, and we'll supply our control units to the OEM. So that's how we've been working with some larger companies as well. Okay, go ahead. No, go ahead. Go ahead. Next one. Next. So there are 2 major architectures that we started off with: the base architectures, and the other hybrid architectures that we have are a mix of these 2. So one is the parallel hybrids, and then the series hybrids. Parallel, the one that we are doing for motorcycles right now. Generally, if you talk about hybrids, OEM's question is about we reach only 20-30%. But in our case, in the parallel hybrids for the motorcycle, we were able to achieve around 70% increase in fuel efficiency from the base vehicle. A base vehicle that gave around 65 kmpl, we were able to reach 115 kmpl with around 10-15% scope of improvement from that. In terms of performance as well, we were able to give 30-40% improvement in performance, which is acceleration. So this is one base, and the next one is a series hybrid, which we are right now using for 3-wheelers and small commercial vehicles. Here, it's a pure EV with an onboard generator, which anyone can do, but then the algorithm and the logics that we bring in, the power balancing method will give us twice the efficiency, at least 80% of the efficiency of the base vehicle. Here, in our prototype stage, we were able to reach around 50 kmpl. So in this technology, like Nasi was saying, it's fuel agnostic. We can use petrol, we can use CNG, biogas, whatever. In one of our three-wheeler projects with a large OEM, we are doing a CNG-based hybrid with them. So from 14, we've been working on hybrids for the last 8 years, and there was an area that we are an expert there in the hybrid controls. So the general question we get asked about when we talk about hybrids is, what are you doing for EVs? So last year, in less than a year, we said, okay, hybrid control units are something that we've been, so these are some of the architecture things. So hybrid controls are something that we've been working on for a long time, which are engine control. We had to control the motor, we had to control both the power systems together. So we felt that is another area that we have an expertise on. So what we did was, we separated the engine control from the hybrid control that we had, the EV control, wherein we have now vehicle control units and motor control units that we are currently doing. So right now we have two areas that we are working on. One is powertrains, which is specific to hybrid powertrains, agnostic to fuel. Second is the control systems, the VCUs and MCUs that we are currently doing. We like vehicle controller for hybrids as well as EV, which can be implemented on hydrogenized fuel cells as well. Right now, we are going to work on a project with a research organization on VCU for a hydrogen fuel cell. So in terms of what we are trying to innovate to do is that embedded hardware is all the same, anyone can do. But Nitish was talking about safety, the fire hazards and everything. If you look at Europe, we cannot go and talk to any of the European companies without talking about ASIL or ASPICE there. So here what we are doing is, most of the companies we talk to, they compromise between cost and quality here. So that is the reason. Chemistry on one side is an issue, but the BMS and everything, if you are following some of the ASIL standards and everything, then obviously those safety hazards, the hazards can be brought down. What we are doing in terms of VCU is something that will sit as a master controller over all the subsystems. Now some of the people talking about this, MCU can be a VCU, but that cannot happen. According to 26262 standards, VCU has to be a separate master controller that will sit above every other ECUs of an electric vehicle. So in terms of process innovation is what we are doing right now. We are trying to implement ASPICE standards. We are going to reach level 1 in the next 6 months. We are aiming level 3 in the next 1.5 years. AutoSAR stacks we are bringing in. We are bringing ASIL rated components. In our two-wheeler project with one of the larger OEM, it's an ASIL C rated controller that we are doing for hybrids. Our VCUs as well will be ASIL rated. So the major core focus of the VCUs that we are developing is safety, performance and maintenance. So that is the main intent of a VCU. But today there are some discrepancy or some misconception about VCUs. VCU, right now we think it's IoT device, but it's not IoT device. VCU has to be a safety device that sits in an EV. So that is what we are currently working on, and we are bringing some of the intelligence from IoTs, unsupervised learning that we use in our hybrid vehicles being implemented in the VCUs we are developing. There are multiple engagements that we have with larger companies, some research organizations where we are doing the VCUs as well. So this is what we are working on. As a technology company, we are building our capabilities on design, development, prototyping, and we have partners for manufacturing. So we work with OEMs in developing or integrating our solutions onto their final platform, wherein the OEMs will take it to the market, we'll supply the controllers alone to them. So, thank you.